thank you very much for the introduction. That allows me to skip 2 slides. As mentioned, I work for JPL and have been heavily involved in model-based system engineering for more than a decade. I worked a long time on telescope and instruments. And here is the list, and I worked a lot of time with Luigi, who is also online back at the European Southern Observatory. At JPL, I've been involved in a number of space missions, helping the projects to move gradually to a model-based system engineering environment. And as you mentioned before, I lead the team that is responsible for providing basically the digital infrastructure for model-based system engineering and analysis. So where are we? So we are located in Pasadena, California. It's still dark outside. We are a so-called federally funded research and development center. So we're NASA-owned, but funded and operated by Caltech. So we're the biggest division of Caltech with around 6,000 employees. You see the picture there. The first few years, I didn't see the snow on the mountains. Last year, I think I did, and the year before. And now it's more like smog because of the fires. Well, it's getting better. Here is an overview of our past missions with all the robotic space missions from landers, orbiters, surveyors, and rovers in particular. And the most prominent one, which is on its way to Mars, is Mars 2020 Perseverance rover. And let's cross our fingers that it will land safely there. So I've been building control systems most of my professional life. So I come from the side that I've been using modeling from the very beginning to produce something, right? I have to deliver a production system that operates some machine typically. So I will drive that presentation from this perspective. So why do we want to have an executable model at all? And in particular, why do we want to have it at system level? Because most of the system engineers, in particular, not in particular JPL, I think at JPL also, the main tools are PowerPoint, Excel, and Word, right? And maybe some requirements management system. And what I often observed is that the behavior and what the system is supposed to do in terms of operations comes very late or is described in some narrative. So to have an executable system helps us to describe that system much better and to gain some understanding before we actually start building it. We want to validate it in the requirements and the behavior in the system model, and we want to understand those requirements better. Usually they come in some text blob, and they are, of course, super ambiguous, but helping with the system level model, we can formulate it in a more precise way. And then we want, of course, to analyze the as-designed system, how it reacts to user interaction, to test data, scenarios, and certain analysis related to budgets, like error budget, resource budgets, and timing constraints. So we want to also to explore not only the sunny day behavioral system, but also the rainy days. So what is not desired by injecting faults and see if the design can cope with that. And before we start actually implementing it, to check the consistency in logic of the design as good as we can, because there's always time constraints, of course, and you can only do so much. We want to understand the roles of the different components in the system at the logical and the physical level. And we strive for having a kind of consistency across all these artifacts that we produce, the model, the code eventually for a control system, the documentation, simulation, and analysis. So That brings us to the topic of model-based system engineering. And what is model-based system engineering? It tries to formalize all the things we do, from requirements management, design capture, analysis, verification, validation, and document everything properly. And as I said, the many tools are Excel is a prominent one, and PowerPoint, and that is not super formal. So you get a lot of inconsistencies, duplicates, and so on. Usually you use some system modeling modeling language to do that, for example, SysML and or Modelica, and some method like OSAM, the object-oriented system engineering method. So those three things are coming together and try to carry out your activities and tasks with supporting modeling techniques. So this terrible picture is from the early 2000s. It's where I kind of started to get involved in model-based system engineering, where the big promise was, okay, today we have all these documents as in the artifacts I mentioned before, but in the future we will have only models. I mean, moving from a document-centric to a model-centric world, to have our requirements for interfaces, the system design, and so on. And I pitched that a lot of times, but of course it doesn't work. The documents won't never disappear. People want to look at the documents, but we want to support them and relate them and actually create those documents from the models. And that's a whole other different topic that's OpenMB related that I will talk about also a little bit. But the models have started to play a much bigger role in this exercise. So before we go into what the current state is, let me put on my archaeologist hat a little bit and share my experiences from back in the days, where I think many of you are much younger than I am, so might not even were born at that time. So the first time I got into touch with something like system level modeling when I worked at Alcatel in the 90s. They had some system that was based on the specification design language, from which actually the UML sequence diagrams originated. And it was a kind of a nice system with graphical and textual representation. You had some semantic checker, a report generator, a code generator, which didn't work. And but you could specify your system as an interconnected set of abstract machines. And it was used for telecom systems to specify them. But it was super cumbersome to use. It was one basic state machines and sequence diagrams, and that was about it. The second time I got into touch with something was when I worked at CERN, and they used the system which was called Foresight, and it was really very comprehensive. You could capture your system requirements and design, and you had a graphical executable GUI where you could see all your state machines executing. You could combine it with some action language which was derived from Ada, and it was a discrete event simulator that was used to model basically the experiments of the LHC with 10,000s of channels. And it was nice. I mean, back in the day, almost everything you needed. But then it died, and it died because it was a proprietary system. It did not integrate, it was not open, so it just disappeared. And then it took a while. Right? So here's some history. So 94 was the Neutrino thing, UML 97, and that's basically, I mean, before that I used all the stuff with Code Jordan, Grady Booch, all these methods, and then I jumped on UML. SysML came 2007, so 10 years later, and still both of them initially it was mostly boxes and lines, and there was, as far as I understand, also no intention to have to have it executable. Right? It was a description, an English description of of the semantics, but that was not really sufficient to build something. But people still build something with it. somehow the big change on the professional level was when XML came out, the state chart XML standard by the W3C, which thereafter was in 2010, and that's when Luigi and I started to use a more model-driven, or actually a very model-driven approach to develop our systems, right? To have the model and to produce something that actually runs on the target system. It got standardized in 2015, so it took also several years. FUML improved the situation with UML quite a bit, but still, and then it took still a number of years to get the precise semantics for compositional structures and the precise semantics for state machines. And thank you, Ed, for that. He is on the call, I think, as well. But quite a bit. And in between, people did something else, right? They had to fill in the gaps of the specs, because they wanted to provide a tool that you can execute and simulate. So 2011, another tool came out that made the first attempt of being like a framework, not just a specific tool. And it took, again, like a number of years to get it to maturity. But I want to highlight three things which are important here. First, that it's multi-engine and pluggable. So it's a framework that provides you the ability to plug in different simulation engines and different languages. And it's standards-based, right? So it implements the SXML, PSSM, FUML, and SysML standards. And that is kind of very important. That's the big difference to the other tools that I mentioned before, to be standard-based and open, because then you can rely on something. But of course, the specs are imperfect. So the gaps have been filled by the tool vendors. And that is a problem from the practitioner side, because one tool does it a little bit different than the other one. Right? So I will get to that in a second. And yeah, so with that framework, that was 2011 was the first attempt to kind of do some kind of MUS system model based on SysML. And it demonstrated then that you can integrate state machines, parametric models, activity and interaction models, and they can work collaboratively to describe your system, to specify your system, and to analyze your system. And that was kind of very encouraging, because you had a standard-based open environment that you could work with. Of course, it took some time to mature. So what's the current state of practice? So at JPL, so here's some selected JPL applications. The 30-meter telescope, SMAP, which is a satellite, Psyche, which is flies to an asteroid, the Europa Lander mission concept, Mars sample return. And what we do there mainly is to capture operation scenarios. So what's going to happen if the lander lands on Europa? What will it do if it will land on ice in deep snow? How can it examine the site and take samples and so on? And to model that and capture that, we use activities, state machines, parametrics, and sequence diagrams to produce a number of artifacts like interface control documents, functional design documents, analysis reports, and also code eventually, hopefully. So there is this slow and still slow transition from writing up everything in a document before and having a model to capture it. Still, the engineers sketch many things in Visio first or in PowerPoint, and then we help them. So my team helps them to use our environment to formalize that workflow. Right? They sketch something up. We help them to formalize it in some SysML model, and we make it executable. We help them to make it executable, so they get interesting insights into their specifications. So I picked two examples, and I picked those two because one is actually the whole model is open source, which is the 30-meter telescope, and there we started, yeah, maybe 5 years ago, about 5 years ago, for one subsystem, a fully model-driven approach overall, and then expanded it into other subsystems. But it works in the kind of hybrid approach. Right? You use traditional system engineering for your deliverables, and because people are used to it, and you can trace things more simple. And we use the model-based approach to mostly or almost exclusively to understand the behavior of the system, right? For which is kind of was the stepchild for many years. The behavior was always kind of a stepchild, and to have this rich capability of modeling and executability to represent this kind of complex systems and combine the two. So what are the MBC objectives of that project? So we capture the operational behavior, identify the involved subsystems, right? Because sometimes you don't know, you start somewhere with some functional component, and how does it interface with other components, what are the other components it has to interface to, what are the interactions between those, to define requirements, so like timing requirements for algorithms, and also interfaces to other subsystems, to create a fully executable SysML model. And we have successfully achieved that with all the problems that appear. But we have a fully executable SysML model that is using state machines and activities, and also sequence diagrams. And that enables us to analyze the system design, right, and verify the requirements for different aspects. How much power does it consume? What's the timing or duration of all these operational behaviors? Do they satisfy the requirements, at least of the S-design system, for error, to calculate error budgets and so on, but also to produce engineering documents. And the goal was to use only standard languages and techniques and commercial off-the-shelf tools where we can, and to avoid any kind of software development, because it's a very, very small team with a lot of work, so there is not much room for experimentation. So here is one thing that comes out of that. It's a timeline produced by the simulation, where you see basically all the components involved in one scenario, in the states they are in, and how long they're in a certain state for that scenario. So why does that help? It helps because we can quantitatively see what the components do, right? And we always needed that information, but it was extremely costly to produce it, right? With PowerPoint and Excel, you can imagine what it takes to produce something like this. I mean, to build a model is also expensive, but that's somehow in the beginning. If it's expensive probably to build that model, but once you have it, it's cheap to update. So when we built the initial framework and identified the patterns, to add new things became a routine. Right? Identify a new use case, capture the use case, model the behavior, and analyze it. So there is a learning curve in the beginning, but it flattens out. The other example is from SMAP, and there it was used to specify the behavior with the target to get a logic design for the fault protection. So if a fault appears, how do you recover from that? How do you identify it? And it was a set of so that's a few years back, 8 state machines with a couple of hundred of states, and we used the executable model to identify the behavior of each component, how they interact, the interfaces, and so on, and to check the initial logic of that design. We also applied, to some extent, model checking to that. And as you can imagine, the state space explodes very quickly. But they could get some reasonable results like five years ago. But I see also now that we can do better nowadays. So we're also working on a framework or a service for model checking to enable that. But the executable model is the key. That's the first thing you have to have, right? So to produce something which is not just boxes and lines. So in that case, in the SMAP case, it also generated like sequence diagrams automatically from the execution. So the system engineers would print them, put them on the table, and look, because they like to print things, and look at which components are interacting, how they're interacting, which kind of messages are flowing between them. So the model represents the system as an authoritative source, right? So we used to do this analysis, but they were expensive. As soon as we have the executable model with specified semantics, we can do them, and we can do it with confidence. So that's a kind of a big step. But of course, there are a number of challenges, in particular with adoption. So my background is computer science, so I can somehow digest all these things that happen in the background, but many people are not, right? I think that the problem with there's a lot of semantic issues, variations across the standards and the tools, and I list here just a few. So if you use one, like some slight subtle difference between SCXML and PSSM, and then across the tool, and then in the beginning you somehow never know, if the simulation doesn't do what you expect, is it a bug of the tool, or is it my model wrong, or is my model in my head wrong, right? So, and I want to focus only on the model that is wrong in my head. I don't want to understand if the semantic is correct, is compliant with the specification, or if the tool has a problem. I don't want to deal with that, but I have to. I mean, I still have to. So you shouldn't have a computer science degree to do that, and particularly if you have Excel and PowerPoint as your main tools. And we see that in other languages as well, right? I mean, Java developers, they don't necessarily know anything about the abstract syntax or grammars, and yet they produce a lot of Java code, and it works, right? And the same thing we want to have for our system engineers, right? We want to have the system level execution analysis to be compatible with the system engineering practices, and that's quite a challenge. So another aspect is code generation, right? You have the executable model. You want to you can simulate it, but now you have actually captured a lot of the semantics. So how do you, in particular for behavior and control systems, how do you bring it to the target? And over I don't know 30 years, as I said, basically starting in the 90s, I've tried to use let's say, code generation, right? Transformation rules and so on, and trying to feed it back to the model if it change code, and there's always something which doesn't work. In particular, the round trip, I think, never worked. And if you actually generate concrete code, right, with some arbitrary rules, and produce some arbitrary code, you have also run in kind of a lot of issues. The code might be hard to understand, hard to debug, hard to change, and you lose somehow. You still have the transformation, but it's kind of a disconnect. So instead, what we would like to have is to have more like the model of a 3D printer, right? You have your CAD model and you 3D print it, and there it is. And if it doesn't quite fit, then you can still, use your Stanley cutter and shape it and update the model to make the model better and produce another 3D print. Right? But it's more like a different, and for the executable model, it's similar. Right? You want to have the same model that executes running on the target system. We don't want to have anything between. Right? We want just want to view it as a different level of execution and maybe serializing in a different way. And that's kind of different from generating code. And the first step in that direction was the use of SysML, because you have your simulation model. You can have you use the operation semantics of SysML to simulate it, but then you produce this XML file, and you use an execution engine which you can test as much as you want, and should just load that same model that you created and simulated and run it on the production system. So that's more the direction we want to go, and not produce thousands of lines of code. And that enables us to do a lot of things. I mean, we can change that file easily, and like we can change the 3D printed part and improve the model later on. Right? So that's more the way we want to go. So what are the enabling technologies? Right? Where are we heading to? So the first thing is to think about let's say the traditional V model. Right? You have all the left leg, you have all the requirements flow down, then you implement something on the right leg of the V. You have all the verification and validation activities. And nowadays, often you try to, there's documents flowing down and test plans flowing up. But what it really has to be, we have to connect those things along the legs, but also between the legs with a set of models. Right? And those models have to be connected as well. Right? So we want to drive it down from the science model to the subsystem models and to the implementation. Right? So we want to have requirements management model based, the architecture design, the analysis, the V&V, right? And ideally also the implementation. So the model becomes the connective tissue in all these exercises. Right? So nowadays you might have some model actually. So people build models, but then they copy paste everything into a document and give it to the person, for example, for flight software to implement it. Right? So you have immediately a disconnect. And then we produce test cases based on that code maybe. Instead, we want to have the model that connects all those things, right? So we can keep the documentation code, the test cases, and the analysis connected, and they're not anymore a disjointed picture. Right? So that's this transformation that we are transformation in terms of the culture, right, and the technology we want to work on. That comes, so another objective is to build some end-to-end goal-based executability framework. So you have like produce a system model of the control architecture that also enables autonomy. You have an executable set of requirements, you clarify the understanding of the control architecture, perform the analysis and build transformation. And the analogy I draw here is with Google Maps. Right, so almost everybody, at least in the US, uses Google Maps. You enter your destination, Google figures something out and directs you by go. Okay, turn right, turn left, go straight, and you follow these instructions. You're becoming Google gives you a goal, and you try to perform this goal to your best abilities. If you can, you try to turn right at the next traffic stop. And you do whatever is necessary to do that. So you're trying to achieve that goal. And if you can't, then Google will figure out something else, right? You miss the right turn, and Google rerouting. Well, it recalculates the network of goals and gives you new directions. And that's also very important for a control system, right? Instead of procedurally prescribing every step that you have to do, which is hard to change, you want to move to a more goal-oriented framework. But it should go the whole way, from the design, analysis, simulation, to the implementation. The second part is an environment, a model-based engineering environment. And a key role plays there the OpenMB community. And today there's actually, in 45 minutes, there's the first OpenMB workshop at the models. We had a few at the in COSI, at the International Council of on System Engineering, with a lot of participants from the practitioner side, from industry mostly. But this community built over the last, let's say, 5-6 years, and they all have the same goal. They all need a model-based engineering environment, right, to handle the complexity of the increasing complexity of the systems and do this transformation of the system engineering culture. And it's the community for software and for models. So it provides a number of apps and services that build the core also of our digital infrastructure to manage models, to close the gap between engineering artifacts and the documentation you have to provide. But it also contains or people contribute models that can be reused, right? And it's a very good forum to exchange ideas and the challenges that we all face. So the community has been growing quite a bit. We are now over 400 members with participants and adopters all from various industries, as you can see, aerospace and automotive, but also academia. So that has become a key element in this strategy. And the goal, the vision of OpenMB is to produce this global engineering ecosystem. Right? We want to have this connected ecosystem because we are not only in an isolated place, but we, for example, JPL has to interact with other NASA centers, also with ESA across the ocean. And they all produce some engineering artifact and documents, and often disconnected. And there are two elements that are part of this strategy. One is Jupyter as a central piece for multi-language capabilities to connect modeling and engineering, and SysML v2. And Ed, I think Ed gives a keynote today in the workshop. I think there was a tutorial on Friday. So SysML v2 has evolved, I think, over the last years, really in a very good direction. I think we have already now a stable specification, or a good specification, that makes me very, very hopeful for the future. But this engineering ecosystem, you can compare this engineering ecosystem to the web. Right? When I worked at CERN in 1990, and the first web server went online, and with OpenMB, the first engineering server went online. So that's so I invite you to join the community, to attend maybe the workshop today or the OpenMB event tomorrow at the Industry Days, where a number of the community members will present their work. Jupyter is a key piece in this strategy as an analysis and visualization hub for models. It provides this very rich, interactive, exploratory, and web-based environment to connect modeling, engineering, data science, and a number of other things. SysML v2 is also a key element in this strategy. It's not anymore constrained by UML. It has a new meta model. It's based on formal semantics and has a robust visualization with a flexible view and viewpoint specification. And also, most importantly, it provides a standardized API to access the models that you produce. And we also have, meanwhile, let's say in the reference implementation, an integration with Jupyter. So you can put together in Jupyter, create your model, visualize the model, and combine it with documentation. And hopefully in the near future to actually analyze it also. Another key element in all this executability and simulation world is FMI. I'm not sure when it was initiated, but I think it maybe 10 years ago, and I think it was Daimler. Meanwhile, there's a whole lot of organizations supporting it and 100+ tools, and it enables sharing and integration of different executed models to enable co-simulation. So that is also in this world of there will be not the single model that will do everything, but it will be a federation of models to enable you to do the analysis that you do, and FMI plays a key role in that. And for SysML, for the current SysML, I think we haven't been able to produce FMIs. I hope with SysML v2 it becomes much easier to produce a functional mockup unit that you can run in a co-simulation with other models like Modelica, for example. Modelica is based on FMI standard for executability, so it would be nice to combine those two. Another aspect is the model management, right? So it has been and still is a big challenge to how do you organize your models so that you don't get crazy, right? With all this, if it becomes too big, it becomes unmanageable because you cannot configuration version control it properly. If you divide it up too early, it's hard to manage those dependencies as well between the packages. So Conda shows how that should work. It could work from the Python world, and we want to have something similar for the models. I want to have some framework, and Conda probably could manage that to manage the dependencies and of my self-contained models. Right? I want to take something, so here it is, reuse it, integrate it into your model without trying to disentangle it from all kind of other things. So to enable this distribution of self-contained packages and model reuse, right? So to broadcast these models, like on Conda channels, you broadcast Python packages. So this SysML v2, Jupyter, Conda, and the FMI are kind of key pieces in that picture of the future model-based engineering environment. Also, everything in related to executability. So here you see, and that's my final slide, the next generation system engineering dream car. Jupyter in the center, SysML is the chassis, SysML v2 is the engine, FMI and Conda are the wheels, and OpenMBE is the driver. So thank you very much for your attention.